So any questions before we jump into more about timers? We're going to go through some sample code related to timers. I want to do some stuff in mplab and not only write some code and analyze it, but also show you some of the tools you can use in mplab to record your observations and then hopefully put those into your lab reports. All right, cool. Yeah, definitely come by lab hours. That's definitely a good time.
Yeah, I was about to say, definitely after lab hours, because I have questions about the math behind this.
Okay.
And I have another question, as I was doing the last lab, and based off of delays, is there a way for... I noticed that there wasn't a way for me to actually see if the delay was working at the right time, because it would just continue running even if the process ended.
Well, you can set a breakpoint at the point where you think the delay should be ending. And yeah, and I'll show you some tools this afternoon that you can use to actually like monitor time in the simulation.
Okay.
And those will be helpful.
My experiment was based off of like trying to figure out if the delay was actually working at the right times.
Oh, okay.
Like different numbers, and I was like, I can't make this work the right way with my current tool.
Yeah, unless you single step a lot and count forever. So yeah, we'll go over some tools that make that easier. All right, cool. Go ahead and send me a an attendance ping. Let me know that you're here. Awesome, good stuff. All right, so so we dug deep into timer 0 on Tuesday, and we were looking at the mechanics of how you set up the timer to do something, and largely looking at the options for adjusting how long of a timing event we want. So what are some of the ways we can control how long it takes before a timer interrupts us?
If we need to wait 255 cycles or less, we can basically just enable the timer. But if we need to wait longer, we can enable a scaler.
Okay. So one way is to pick a value to load into the timer register initially, right? Because it counts up from there until it overflows. And then another way, if we want a longer time interval, is we can use a prescaler. Any other options?
You could set timer to 8 or 16 bits.
Yeah, we can say the whole thing is either 8 or 16 bits. And this initial value, if it's limited to 8 bits, it's, you know, as someone said, between 0 and 255. If we make it 16 bits, we can go up to 65,000. So you have a much wider range of potential delays. What's the other thing that affects the time it takes, like the amount of wall clock time that it takes before an interrupt occurs? The thing we don't usually talk about. It's a little subtle. But the clock speed, right? Because all of this is triggered off the notion of how many instruction cycles we want something to take. But depending on how long an instruction cycle is, that, you know, affects the actual wall time. Default PIC processor, the physical chip, if you just power it up and don't do anything else, the default clock speed in there is, it's actually 31 kilohertz. So 31,000 ticks per second. We usually do 32 because it's easier to divide by 4, but it's 31,000 kilohertz. The simulator has a default system clock speed of 4 megahertz. And so the instruction clock, if the system clock's 4 megahertz, what's the frequency of the instruction clock?
1.
1. How do you know that?
Because it takes 4 instruction clock cycles for one system.
Exactly.
Clock cycle. Okay.
Yeah, so most instructions execute in 4 ticks of the system clock. And so you divide your system frequency by 4, you get your instruction frequency. So if we have a 32 kilohertz system clock, that's divided by 4, 8,000 instructions per second. The default simulator settings in mplab run your code as if it's running 1,000,000 instructions per second. So when we start looking at tools in mplab that will let us look at how many milliseconds or microseconds have passed, it's using this notion of 1 megahertz. So when you write your code for lab 5, where you're dealing with very specific timing intervals, you're going to want to use this idea that the system clock is running at 4 meg, and so the instruction clock is running at 1.
Have 4 meg or 1 megahertz?
So 4 meg is the system clock, 1 meg is the instruction clock.
Okay.
So 1,000,000 instructions per second.
Okay, because you just said 4 meg for the lab 5.
So 4 meg for the system clock. 1,000,000 instructions per second is the critical thing to remember.
So, which one for the lab? 4 or 1?
Are we talking about the system clock or the instruction clock?
So either?
So the system clock is 4, the instruction clock is 1. So both of these correspond to the same speed of the processor.
Does it depend on the instruction you're giving your lab at the time when you're still going through the process?
Not technically. When we talk about the instruction clock, we're talking about most of the instructions: increment, clear, add, complete in 4 ticks of the system clock. So yeah, there's some instructions like move FF that'll take twice as long, or go to that'll take twice as long. But when we talk about how many instructions execute per second, we're thinking of sort of that minimal instruction, the no-op, if you like. So in the simulator, main thing to remember: 1,000,000 instructions per second. And we don't usually talk about the system clock a whole lot. It's there, but mostly we just divide by 4, and that gives us the instruction clock. And this is the one that we use for all of our calculations, our delay loops, our setting for the values for timer 0, and so on and so forth. We always care about the instruction clock. So the frequency to worry about in lab 5 is 1 megahertz. All right, so, yeah, question? So timer 0, this is a pretty good picture of it, right? And it's basically, it's a register, TMR0, and there is no register called TMR0. There's a timer 0L and there's a timer 0H. And if we're in 8-bit mode, we only care about timer 0L. If we're in 16-bit mode, we care about timer 0L and H, right? But sometimes you just see TMR0, and it just means, whatever the register is that's counting for timer 0. It could be 8 bits, could be 16 bits, right? So in diagrams like this, you'll see names that may not match the actual special function register names. So this is either the 8-bit or the 16-bit timer register, right? And in 8-bit mode, it's 8 bits, right? And it basically just keeps incrementing. And the thing that increments it is, well, it's either the system clock divided by 4, it's the instruction clock, or it's something coming in from an external pin, and it potentially goes through a prescaler, and so on and so forth. In 16-bit mode, the picture looks almost exactly the same, except for this business over here. And what's happening here is that, timer 0 is a 16-bit register, so here's the low 8 bits. Here's the high 8 bits. It's called timer 0 high byte. Here's the thing we actually get to look at by using, our special function register, TMR0H. They're separate creatures. And the funny thing about playing with timers is, time is always moving forward. And if our timer is on and we were to read, you know, timer 0L, and then read the high byte of the timer, it's possible that something rolled over in between there. And so the setup is, when you read the low byte, the processor takes a snapshot of the high byte also and saves that for you. So that effectively you're reading both of these at the same instant in time. And when you write the high and the low bytes, well, you write into this register first. And then when you write the low byte, both of these 8-bit registers get written into here simultaneously. So this business of make sure that you read the low byte first and write the high byte first is about avoiding these kind of edge cases where, suppose your high byte was this and your low byte was this, and let's say your high byte is 2 and your low byte is let's say it's 254.
Do you think you could go over setting up timer 0 one more time? I tried to do it in the custom experiment for the last lab, but I couldn't quite get it to work.
Okay, yeah, definitely. I'm going to go through that in mplab actually.
Okay, good.
So if timer high is a value of 2 and timer low is a value of 254, and you were to just read the value of this, right? You might read, you know, low is 254, and it takes a few cycles to read, and so this increments to 255, and it increments and rolls over to 0, and this changes to 3, and it increments to 1. And now if you read the high byte, you're going to read a 3. And you're going to think that when you read the timer, the high byte was 3 and the low byte was 254. Well, that's way off, right? In fact, when you started doing the read, the high was 2 and the low was 254. So when you read the low byte, the high byte is snapshotted and loaded into a holding register. That's what timer 0H is. If that made sense, cool. If not, don't worry about it too much. But this is why we do these reads in these very particular orders. All right, so let's look at timer 0. And then we'll talk about timers 1 and 3, and then we'll go into some code. So timer 0, main thing they usually summarize. Yeah. So timer 0L, timer 0H, those are your two 8-bit registers that you load the initial value into, knowing that each time that the register increments, it's going to get closer to overflowing. And when it overflows, it's going to request an interrupt. So if you want an interrupt very soon, you put a very high value into these registers. If you want an interrupt very far in the future, you start these off at a low value. And you translate how long you want to wait into the number of instruction ticks, and you set this value for timer 0, L, and H, so that after that many ticks, it hits the overflow point. And then the control register, so bit 7 turns the timer on, that's its default value, but if you want to stop it, you can set this bit to a 0. This bit chooses whether it's an 8-bit timer or a 16. 8-bit, you're only using timer 0L. 16, you're using L and H, and it overflows at 65,000. 8-bit overflows at 256. T0CS, we're always going to set to 1 for this class, which says, sorry, we're going to set it to 0, which says the clock is coming from the instruction cycle clock. So that's what's causing it to tick every instruction. If you leave this at its default value of 1, then it ticks based on a signal going into an external pin. All right, TOSE we don't care about. It only affects us if we're setting this value to 1, and it says does the clock tick on the rising or the falling edge of that external signal. And then these 4 bits control the prescaler. And basically, if you make this bit a 1, this PSA, then there's no prescaler assigned. It's just one instruction cycle, one increment. Second instruction cycle incremented by 2, and so on. But if you want to delay how long it takes to increment, you can set up a prescaler from 2 to 256. So you make this PSA bit a 0, says the prescaler is assigned, and then you set these 3 bits, PS2, 1, and 0, using this table to say how much of a prescaler do I want. If you set the prescaler to be 16 by loading that bit pattern in, then after 16 instruction cycles, timer 0 increments by 1. Another 16 cycles, it increments a second time. Another 16, it increments a third time. So it's counting 1/16 as fast as if you have no prescaler. It's going to take 16 times as long to overflow. Does that make sense? So let's look at timer 1 because it's almost the same business. So timer 1, so you turn it on with bit 0 of T1 con. So again, don't use magic numbers. If you want to set this to a 1, do bit set file T1 con, comma, timer 1 on. Everyone's homework looked really good, by the way, as far as using these mnemonics to set and clear bits versus using the whole bit patterns in the earlier question, and that all looked really good. A few cases where sort of the higher idea of interrupts might have been confusing, so I left feedback around that and come and talk to me. But the code people are writing for that looked really good, so keep that up. As we work with timers. So set this bit to a 1 to turn the timer on, right? And by default, this is always the default value shown here. This is a 0 by default. 0 means the timer is stopped. So timer 1 is normally not running. Timer 1 CS, that's the source for the clock, that defaults to a 0, which is the internal clock. System clock divided by 4, that's your instruction cycle clock. If we want, we can get this clock from an external pin, right? If we're using the system clock, if this bit is a 0, then this next bit, T1 sync bar, is ignored. That's used to synchronize if we're using an external clock. And then timer 1 oscillator enabled or shut off. The oscillator, inverter, and feedback resistor are turned off to eliminate power drain. So timer 1 OSC, I don't think we need that because we're using the internal clock. So you're fine leaving this bit set to a 0. And then we've got prescaler possibility. So you have 4 prescalers, 1 to 1, 2, 4, or 8. It's not as many options as timer 1. And then system clock status bit. System clock is derived from another source or from timer 1 oscillator. I don't think we care about this, so you can probably leave it at 0. And then this bit is a little weird. The read 16. I would go ahead and make that a 1 to do 16-bit operation. And I think, I'm not 100% sure about this, but from what I've been able to discern, I think that basically turns on this kind of behavior, where you read the low byte first and write the high byte first so that you can synchronize the 16-bit operations. So that's timer 1, right? Basically the same thing. And it comes with its own sets of registers. So the interrupt enable is in PIE1. The interrupt flag to tell you it's requesting an interrupt is in PIR1. And the timer 1 IP, the priority setting, is in IPR1. And so you manage your interrupts like that, turn on global interrupts, high or low priority here, and always set that IPEN bit in the Archon register, bit 7. All right, so same deal as timer 0. You load a value in the timer register, it counts up. When it overflows, it'll request an interrupt. If you turned on this interrupt enable bit, those interrupts will go through to the global interrupt request system. If you've enabled global interrupts at the appropriate priority and you're not processing an interrupt right now, it'll request an interrupt and you'll jump to either vector 8 or 18.
So the timer interrupt isn't considered like an external peripheral interrupt, right? It's an internal thing?
It's an interrupt. I don't think we need to worry about whether it's considered a peripheral or an internal. Those notions are older processor compatibility concepts, and I don't know what the distinction is between a peripheral and a non-peripheral interrupt.
Yeah, I was wondering when reading about GIEL and GIEH with ENGR1.
Yeah, and so the reason we don't have to worry about it is because if you set up that that 7th bit in in Archon. If you set up that IPEN bit, if you make that a 1, it's using priority levels on interrupts. And if you enable priority levels on interrupts, so remember IPEN is a 1. So when we look at bits 7 and 6 of INTCON, we only care about this definition right here when IPEN equals 1. 1 enables high priority, 0 disables all interrupts. And bit 6, when IPEN is 1, 1 enables low priority, 0 disables low priority. So those are purely for high priority, low priority, enable or disable. If we don't change that IPEN and we leave it at a 0, then we get into this business of, you know, bit 6 is enabling unmasked peripheral interrupts, and bit 7 is doing all unmasked interrupts. And that's how interrupts were set up on a different series of processors, and so they left this in for compatibility. But your life is a lot easier if you just think high and low priorities. And most sources can be either high or low. There's a few exceptions. And when we set that bit 7 IPEN of the Archon register, then we're just thinking of this definition for global interrupt enable high and this definition for global interrupt enable low.
I have a quick question.
Sure.
So, when the timer goes off, does it jump to location memory like 8 or 18?
If it's a high priority interrupt, it'll jump to 8. If it's a low priority, it'll jump to 18.
Okay, cool.
And timer 0, is timer 0 high, low, or selectable? And I'm asking you to stall while I'm looking it up, because I don't remember. I think it's just high. Yeah, I think timer 0 is always a high priority interrupt. But timer 1, I believe we can select. So yeah, we can set that timer 1 IP to control timer 1. Similar to how int 0, the pin is always high priority, but int 1 and 2, those pins can be either high or low. Oh, that was another quickie on the homework. Worth mentioning. Why is this being troublesome? So those interrupt pins, int 0, int 1, int 2, if you look at the beginning of your data sheet, right, int 0 is right here on pin 8, that's RB0. Int 1 is on pin 9, that's RB1. Int 2 is on pin 17, that's RB2. So your interrupts are coming in on those first 3 bits of port B. And a lot of people, in fact most people, set up port A instead of port B. Not a big deal, it's just something to be aware of. And the only reason that you know that it's port B instead of port A is from looking at this figure. So that's your only clue to it. Alright, so let's look at timer 3, and then we'll come back to timer 2. So timer 3 is a 16-bit timer, so you can't choose 8 or 16. It's always 16 bits. You can set this bit to a 0 to do 2 8-bit operations, so same as we're used to. It's got a choice of prescalars, 1 to 1, 2, 4, or 8, selectable by these two. You can choose the source to come from the instruction clock. So same thing, that's timer 3 clock source. Set that to a 0. The sync pin is ignored. The CCP1 we don't have to worry about. And then timer 3 on, set that to a 1 to turn the thing on. And it looks, you know, very much like every other timer we've talked about. Source of oscillation comes in, prescaler comes in, gets selected with something else, and is used to bump up a 16-bit register. When it overflows, it requests an interrupt. And same thing, interrupt flag, interrupt enable, interrupt priority, those are bits in these registers. And your global interrupt bits as usual. So all of these subsystems we talk about, they're usually short chapters in the data sheet, but they give you kind of a general synopsis of it. They take you through the details of the registers that are specific to that subsystem. They usually show you a block diagram of it. They talk about it in words. And then they usually have a summary of all the special function registers that in any way, shape, or form relate to this. Right? Even though the interrupt register is talked about in the interrupt chapter, right? It's involved when you use timer 3, so they list that in here also. The data sheet's really useful. I don't recommend printing it out. If you printed it out, you know, you could write notes in the notes section after each one and so on, but it's a big manual. But definitely get to know your data sheet pretty well, because it's got all of the answers. All right, so let's talk about timer 2. Timer 2 is the unusual one, the most unusual one. Remember when we wrote some code the other day? Well, let me just show you some code. Let's see, where'd my mplab go? Here we are. So remember we wrote some code to set up a timer, and we stepped through and we let it increment, right? So we loaded a value into a counter. I'll put 240 into there. And once we do that, the counter starts incrementing every instruction, and when it overflows, it requests an interrupt. And remember, the first time we did that, when we went into the interrupt, if we just, you know, cleared the interrupt flag and returned, it took 256 ticks before we got another interrupt. Because when the counter register overflows, it goes back to 0. That's what happens when you add one more to the maximum value. It becomes 0. And so the next time, it has to count all the way from 0 up to the overflow value before it'll interrupt. So what we had to do in our interrupt code was we had to take whatever value we wanted our timer to start at and reload that into the timer register. And that's not a horrible thing to do, but it's a bit of a pain. So timer 2 takes care of that for us. Timer 2, instead of starting from, you know, some initial value you load and counting up to an overflow point, timer 2 does something a little different. It starts from 0 and it counts up, but it compares the value of that register that's being incremented to another register called PR2. That's the period register. And when the timer register equals the period register, two things happen. One, it'll request an interrupt, and two, it will reset the timer register.
That's handy.
That is handy. So here's the possibilities, right? Timer 0 is, you know, 253, 254, 255, 0. Generates an interrupt, 1, 2, 3, 4, and so on. And if we wanted to interrupt, after 16 ticks, we need to come in here and we need to dump a 240 into this register so that after 16 it overflows again. Timer 2 starts from 0, 1, 2, and it goes up until it gets to whatever the value of PR2 is. And at that point it generates an interrupt and it automatically goes back to 0. 1, 2, hits the value of PR2, generates an interrupt, goes back to 0. So if you want an interrupt to occur at fixed time intervals, for example, every 10 instruction cycles, you could take PR2 and set it to 10, maybe 9. And as soon as timer 2 hits 10, request an interrupt, and it resets to 0. And so it'll go 0, 1, 2, up to 10, request an interrupt, go back to 0, 1, 2, up to 10, request an interrupt. So you don't need to go into your interrupt routine and manually load in a new value like we do here. So that's the main business with timer 2. You can sort of set it up and forget about it, and it just keeps generating these interrupt requests. And then the mechanics of setting it up are a little different. So we have a prescaler and a postscaler. So the prescaler is 1 to 1, 4, or 16. And then the postscaler is anywhere from 1 to 1 up to 1 to 16. It's got 16 possible values. And then we have 1 bit for turning the timer on, timer 2 on. And the prescaler controls, how many instruction cycle clocks it takes, how many ticks it takes before the register is incremented. And it's an 8-bit register, by the way. So this is, controls how many instruction cycles happen before this is incremented. That's the prescaler. And as soon as it hits the period register value, it resets. And after that many times that it's hit the period register, after some number of those times, it'll throw the interrupt request. So this is what the postscaler does. If it's 1 to 1, every time that the timer register matches the period register, it'll request an interrupt. If you set the postscaler to be 1 to 2, you'll have to get up to the period value twice before it requests an interrupt. So in effect, you can multiply the prescaler, postscaler together and just think of it as one big prescaler. But again, the block diagram will show you exactly what's actually happening. But if you want a 32 to 1 delay, right, I could set a prescaler of 16, a postscaler of 2, and it'll interrupt after 32 times whatever I set the period register to. All right, timer 2 will actually do a lot more than what we just described. Timer 2 is part of a larger system called compare, capture, and something, CCP, that will let us do all kinds of sophisticated training, timing, and so on and so forth. We're not going to go through that in a lot of detail in this course, but there's this whole chapter on the CCP. Capture, compare, and pulse width modulation, enhanced, ECCP. And a lot of this is built around timer 2. And that's one of the reasons timer 2 is in there.
What exactly would you use the postscaler for?
Bigger prescaler value, basically.
Ah, gotcha.
Because 1 to 1, 1 to 4, 1 to 16, it's pretty coarse-grained, and it doesn't let you get, particularly long. And you've only got an 8-bit register, so you need a bigger prescaler value as an option. But this can go up to 16, this can go up to 16, so you can get an effective prescaler of 256, which is pretty good. So 256, and you can count up to 256, that's 65,000 instructions you can have before you get an interrupt request. And this is designed for more or less shorter periods of time. If you want an interrupt every hour, right, who cares if you have to go into your interrupt routine and you have to do a couple of move instructions to reset your timer registers? It's only happening once an hour. It's not a big deal. But if you want an interrupt every 15 instructions, the fact that it might take you, 5 or 6 instructions to reset those registers is pretty significant. So timer 2 is really good when you're interested in very short but extremely precise timing intervals. All right. Good so far?
Yep.
All right, a little bit of a gear change here. I want to talk about something called pulse width modulation, or PWM. So how many people have played with motors? Like at some point?
I know where this is going.
Hopefully people have played with motors, like hooked them up to a battery or taken them apart or hooked up, 25 batteries to see how fast you can make it spin. Or,
The only thing I've taken apart is a vacuum cleaner, and not that in depth.
Oh, okay. Yeah, take the motor apart. Motors are cool. Motors are magical. They're borderline creepy when you think about how a basic motor works. It's all about magnets and electromagnets and using the fact that certain magnets will attract one another and you use that to induce motion. But as soon as the magnet gets where it's trying to go, you suddenly like flip things so that now it's being repelled, and it's all really cool. So one thing with motors is, right, generally, and I'm just talking about a basic direct current brushed motor, so the kind of motor you would find in the labs at school, for example, when we get back in there, or that you could buy, at a hardware store for a couple of bucks. One thing about motors is, the speed is more or less a function of how much voltage you put on. If you put 1 volt into the motor, it'll spin at a certain speed. If you put 5 volts, it'll spin faster. If you put in 1/10 of a volt, it may not spin at all, or it may be that, if you give it a little start with your fingertips, it'll start to spin, but very slowly. So a problem is, if you're using computers to control things, how can you control the speed of a motor? Because our computers, digital logic, they usually put out 5 volts or 0 volts. If you put out 0 volts, the motor's not going to spin. If you put out 5 volts, it's probably going to spin pretty fast. But what if you wanted to spin at like half speed? And you can do things to, generate an analog signal based on a digital value, for example, but that's fairly expensive. So yeah, good physics flashbacks, and yeah, some good ideas in chat. It turns out that if you take an output signal and you turn it on and off, and you hook this up to a motor, most likely, if this is, a reasonably high frequency signal, a couple of 100 cycles per second or something, if you hook this up to a motor, what you're not going to see is motor spinning really fast, motor stopped, motor spinning really fast, motor stopped. Right? That's not what's going to happen. Theoretically, that might be what you'd expect, but when you stop putting voltage into a motor, it takes a little while to stop spinning. It coasts. And when you apply a voltage to a motor, it doesn't immediately start spinning at full speed. It takes a while to ramp up. And so if you put this kind of signal into a motor, what you're going to find is it runs at about half the speed as if you just put in a constant 5 volts. So this would run, at 100% full speed. This would actually run at about 50% full speed. And if you want to make your motor spin really slowly, what you can do is put in a waveform like this. And this will probably run at about 10% full speed. And what I'm doing is I'm putting in, the full 5 volts for a little period of time, and then I'm taking it off and letting it coast. And then I give it a little pump of 5 volts again, and then I turn off the voltage and let it coast for a bit. Another option would be to do something like this. These are all 5 volts at the top. Right? This is going to run probably about 90% full speed. I'm giving it full 5 volts most of the time, and then I turn off the voltage just for a little bit, like a tenth of the total time. And this will run not quite as fast as that, but pretty fast. And so this is how we can control an analog device like a motor with a digital output. All we have to do is be able to turn our signal on and off at a certain rate, and we can control the effective power being delivered to the device. So the frequency of a signal is, you know, how many times it goes up and down in, say, a second. That's what we mean by a hertz or a cycle. How many times it goes up and down in 1 second. Well, three of these waveforms, let's ignore this 100% example, but all 3 of these waveforms wobble up and down the same number of times per second. Right? They all have the same frequency. So let's just cross this one out because it's, oh, I crossed out the wrong one. Let's cross this one out because it's a pathology. So, well, we can just look at these two, right? Same frequency. Right? If this was 1 second or 1 millisecond, right, they'd move up and down 2 times per millisecond, move up and down 2 times per millisecond. So this business is something different from frequency. And this is something called duty cycle. So the duty cycle is a measure of, during the time when a waveform goes up and then down, how much of that time does it spend being up high? So duty cycle is basically the time the waveform is high over time of 1 cycle, which we call the period. So this is the period. It's the amount of time it takes to go, you know, from, say, high to low and back to high. This is the period. This is also the period. This is also the period. This is also the period. They're all the same, right? It's periodic. If we look at the time from one rising edge to another rising edge, that's the same period. That's the same period. If we look at the time from a falling edge to a falling edge, that's from here to here, that's the same period. From here to here, it's the same period. So the period of all these waveforms is exactly the same, which means the frequency is the same. Because we have this relation, frequency equals 1 over t, where t is the period. But what's different is how long during 1 cycle is the waveform high as a percentage of the entire time of the period. So this is high for exactly half of 1 cycle. That's a 50% duty cycle. This is high for a tenth of the total period. That's a 10% cycle. This one that I crossed out by mistake was high for, say, 90% of the entire cycle. That's a 90% duty cycle. This one here, the one I said was pathological, was high 100% of the cycle. So that was a 100% duty cycle. And what's the other pathology? What does it look like if we have a 0% duty cycle? So how do we make this fraction equal to 0?
Make the numerator 0?
Make the numerator 0. That's your only option, right? So make the time that the waveform is high 0. Don't let the waveform go high. So this is a 0% duty cycle. And yeah, it's just ground, right? It's not really a signal at all, but you know, it's technically a 0% duty cycle. All right, so we've got duty cycle, right? Percentage of time that a waveform is high versus the whole duration of a cycle. And it's independent of frequency, right? We can have a 50% duty cycle at this frequency. We could have a 50% duty cycle at a much higher frequency. We could have a 50% duty cycle at a much lower frequency. So two fundamentally different characteristics of a waveform. And you can use this idea of pulse width modulation to change the speed of a motor. You can also use it to change the intensity of an LED, because an LED, what does it do? You put 5 volts through and it turns on. You don't put 5 volts through and it turns off. It's binary, right? It's either on or off. But if you were to put a waveform like this into an LED, it would glow at about half the intensity. So you can get a variable intensity level on this normally binary device by using pulse width modulation.
Yeah, so you can also get music out of it.
And you get music out of this. Anybody remember Sound Blaster sound cards? This is like old school. So they use pulse width modulation to emulate the analog signals that you normally use when you're driving a speaker. They use PWM to approximate that. And they sounded kind of wonky, but you know, your computer was playing music which it had never done before, so it was pretty exciting. So yeah, this is a good general technique. And Lab 5 is going to be about playing around with doing some pulse width modulation on a signal that you're going to generate. And so we're going to go through details of that. All right, other questions on the general concept? So duty cycle, mainly it's just the percentage. If you look at one period, how much of that period is a signal high versus the entire period. 100% is constant 5 volts, 0% is constant 0 volts. Everything in between is, you know, high for a certain while, low for a certain while. All right, and this is what that ECCP subsystem does. One of the things it'll do is generate pulse width modulated signals for you. But for Lab 5, we get to do that ourselves, which is fun. All right, so give me an attendance ping, and let's take a 5-minute break. And then we'll come back, we'll jump into mplab and start looking at some of the tools we can use to analyze these waveforms, and then we'll break that into Lab 5. All right, so I'll meet you back in about 5 minutes. All right, welcome back. Let's play around with mplab a little. So you're going to use mplab, right, as usual for your next lab, but your next lab is about generating waveforms that exhibit this pulse width modulation, and you're going to change the pulse width modulation over time. So a big part of your lab report, your observations, are going to be something from mplab that will demonstrate to the reader that you were in fact generating these waveforms as you were trying to. So so I'm seeing lots of good details in people's labs, right? What I want you to think about on this next lab, right, lab 5, is how to convey that your code worked successfully, right? And at this point, you know, you can definitely assume that the reader understands basic mplab behavior, understands basic PIC assembly language. And so, for example, you know, when you fire a stimulus and it changes an input pin, you don't necessarily need a screenshot and a whole paragraph of text discussing that, right? Our goal in Lab 5 is going to be to generate this waveform that changes at different duty cycles and have the duty cycle change over time. So you're going to want to think about, how do I, you know, convince myself that the code is working, and then how do I convey that in a written report? And that's what you should put into your lab report is the screenshots and the discussion that you know, let the person reading the report understand that in fact your code was working correctly. So there's some tools in mplab that will help you do that, and I want to use just kind of some sample code here from the other day to play around with this. So this is just sort of boilerplate timer code, right? 7F into adcon. I'm going to put this magic number 240 into this file register I'm calling count. It's just, you know, a file register. And that's going to be the value I initialize my timer 0L register to. And I'm setting up, you know, timer 0 is going to generate interrupts. It's an 8-bit register. And when I get the interrupt, I'll take the value of count, put that back into timer 0L. But I'm going to do something else. I'm going to toggle port B. All right, so whatever port B is, that current bit value, I'm going to toggle that. And then clear the interrupt flag and return. And my tris setup, I'm setting up bit 7 of tris B to be a 0. That makes it an output bit. So that if I were to hook an LED up to whatever pin RB7 is, it should blink on and off. So I can build this, and I've got an interrupt right here, a breakpoint at the beginning of my interrupt code. So let me go ahead and run this. And let me add a watch point for port B. So port B you can see is a 0 right now. And timer 0, it reached 255, it ticked once more to 0, it overflowed, requested the interrupt, and it's already gone back up to 3 because it takes a few cycles to generate an interrupt. You have to save the program counter of the next instruction, the shadow registers and all this. So the timer register is a 3, but we're about to do this move FF to put our magic 240 into the timer register. So there's our 240 value. And now I'm going to do this bit toggle on port B. So right now port B is all 0s. And I'm going to toggle bit 7 of port B. So when I do that, I get a 1 right here. Okay, that's the main action that we're interested in. So this code as it's written right now does what? It sets things up so that after 16 instruction cycles, we get an interrupt and port B turns on, that most significant bit. And then, since we've reset timer L to 240, after another 16 instruction cycles, we should come back to our interrupt code. It'll toggle that 7th bit, and it will become a 0 again. So if I were to, you know, step through this by hand, it's going to generate an interrupt. We're going to come in here, and now port B just toggled back down to a 0. And then after another bunch of instructions, we'll generate an interrupt. We'll come back into our interrupt code, and we'll toggle port B, and that bit 7 is a 1 again. Well, so how do you document this? You can explain, that I tick the down arrow, 14 times or something like that. But if these are longer timing intervals and so on, it's not very convenient to do that. I don't have to single step. I have a breakpoint at the beginning of my interrupt code, and so I can just hit this play button, and every time I come in here, I'll be at the beginning of my interrupt, and if I just use that, you can see that each time I come in here, this port B value is toggling, right? And I'm just looking down here at this red, and every time that I hit the play button, port B toggles, bit 7 of port B. All right, so let's look at some tools. So let's go to window. So let me add a tag here. So there's a stopwatch option. So let's go to window. Let's find my mouse. We go to window, debugging, and come down to stopwatch. And you get a new window popping up here, and it tells you cycle count equals, and there's nothing there, and instruction frequency equals 1 megahertz. Okay, that's the instruction clock, million instructions per second. So let me just go ahead and hit the play button, and every time I hit a breakpoint or my simulation stops for any reason, I'll get a message in here telling me how much time has passed since the last time that I stopped. So if I run this, I hit a breakpoint, and it says target halted, stopwatch cycle count equals 23. So 23 cycles, and it's telling me that's 23 microseconds. So 23 cycles have passed. Let me run again. There's another 23, and so on. So that's useful when you're developing your code. If you expect an interrupt to occur after, 100 microseconds, you can put a breakpoint where the interrupt is, and it will tell you how much time has passed. And if it's close to 100 microseconds, you're good. So let's change our code. Let's initialize our count to 200 instead of 240. So is this going to take longer or less time to interrupt if I initialize 200 instead of 240?
Longer.
It's going to take longer because it's got further to go until it overflows. So let me go ahead and run this. So it tells me that it took 76 microseconds before it generated an interrupt. And if I run again, it's going to take 63. And now every time I do this, it's going to take 63 microseconds. Why did that first interrupt take longer? Well, because I did more stuff. I had all of this initialization code in the beginning, right before I got around to setting up the timer value up here. But, every 63 microseconds now. Well, if I initialize my timer register to 200 and it overflows at 256, that should be 56 instructions. It's taking 63. So about 7 instructions longer than I had planned. Well, why is that? Well, that's overhead. That's the fact that when I get an interrupt, it takes 2 or 3 cycles to get into my interrupt routine. And then I reset my timer register, and that takes a few instructions to execute. And so it's taking an extra 7 seconds. So let's go ahead and set our T0con to 100. And let's run this. And now it's taking 176 microseconds instead of 63. Alright, so this is one tool. This is mostly useful for yourself when you're first starting to work on your code to just kind of get a quick notion for how much time is passing. Because you really don't want to step through one instruction at a time. And, you know, some of these instructions take you know, 1 cycle. Some of them will take 2. So you can use this, right? Set some breakpoints and run your code, and it'll tell you how much time has passed until you hit the breakpoint.
How did you get that stopwatch tab again?
So that's
like, what did you have to click on to?
So go to Windows and debugging, and then down towards the bottom is stopwatch.
Okay, cool. Thank you.
Yeah. All right, the other option is the logic analyzer. And the logic analyzer gives you the same information but in a graphical form. And this is a really useful tool. Once your code is pretty far along and you want to kind of step back and see a bigger picture of what's going on, instead of, you know, looking at how much time has passed and comparing it to your notes on paper and so on and so forth, this will let you get a graphical view of basically a timing diagram. And so let me close out my stopwatch window. And to get the logic analyzer, you're going to go to Window, and you're going to go down under Simulator, and then go to Logic Analyzer. And so that opens this kind of squished up display up here. And to set this up, I'm going to hit the little hammer symbol over here, which says Properties, I think, or Settings. So I'm going to click on that. And you have to choose what signals you want to look at. Now I'm toggling bit 7 of port B, right? So I'm going to look at RB7. So I'll come down here to RB7, and I'll double click that to make that selected, or you can move back and forth like this. All right. And properties, you can say, do I want to look at instruction cycles, or do I want to look at real time? Well, they're kind of one for one, but I'm going to do real time because I want to see microseconds. The largest buffer it'll let you do is 10,000 records, which means it can record 10,000 instruction cycles, which is 10,000 microseconds. And so here goes the metric stuff, 10,000 microseconds. So how many milliseconds is that? I'm getting the physics neurons going.
10.
10. You either divide or multiply by 1,000. And for me, I just always do a test case. I know 1,000 microseconds is 1 millisecond, so I must want to divide. And if I multiplied, I'd get like 1,000,000, which seems too big. So yeah, so it's about a 10 millisecond waveform that we can have from here to here. And you can set up colors for different pins and so on and so forth. So I'm just going to say OK. And let me make this a little bigger. I don't think I need this stuff in the bottom. All right, so let's go ahead and run this. And every time that I hit an interrupt, right, I'll get to see my updated display. So here's what I get. Oh, I get nothing. That's sad. Let me stop this and rebuild it. Oh, I'm hitting the wrong button. So I need the play button to continue from a breakpoint. All right. So all right, I broke something. All right, let me stop this. So this garbage can will get rid of your current waveform, and this will reset the X scale. Let me try this
How do you
once
get the
more.
logic analyzer again?
Windows Simulator Logic Analyzer.
Thank you.
Yep. All right. So now every time I hit a breakpoint, I can look at my new display, and you can see what's happening here. I'm getting a nice square wave out, right? And I'm initializing my count to 100. So it's going to take, approximately 156 plus some change cycles before I get an interrupt. And we can look at the scale here, and you can see, from 0 to, well, it's 180. And then we got an interrupt and toggled the RB7 bit, and then we got up to time 340, and it toggled again. And then we came out here to 505, and so on. And so there's a nice, sort of visual presentation of what your output waveform looks like.
Just a quick question. What's the instruction clock again of mplab? Is it 8?
So the instruction clock is 1 megahertz.
Oh, 1. Okay.
Yeah. So this time that it's showing us in microseconds is also just the number of instructions since the beginning of time. So 1,000 instructions or 1,000 microseconds, which is 1 millisecond. And you can keep running this, and it will hold up to 10,000 microseconds. So we can get a pretty squished up waveform. And then when you get up to 10, it's going to start sliding my scale, and this left side will scroll off the end. And now we're just seeing a fixed 10 millisecond window. All right. And if it's not working for you, hit the garbage can, hit the reset button. That seems to help. All right, so one more tweak on this to illustrate this. Let's change the frequency of our waveform. Right, we're generating a waveform. It's high and low a certain amount of time. The amount of time is determined by this variable count. In this case, we initialized count to be decimal 100, and so that determines how long it takes to interrupt. What the amount of time is, the signal's high and low. That's the frequency. Now it's a 50% duty cycle. It's always high and low the same amount of time. But let's change this frequency. So let me do one more thing down here. When we get an interrupt, before we go back, let's change the value of count. So if I add 10 to count, right, the next time that I get an interrupt, I'll put a bigger value into my timer register. It's going to take less time to interrupt after that. So as this code runs, I should be generating a signal that goes high and low, but it should be getting higher and higher frequency. Does that make sense? And this is just, something we're doing in our code. We're just saying, well, count is how long it's going to be high or low. Let's just change that. Let's change it by 10 every time that we go either high or low, and that will effectively change the frequency. So let's go ahead and take this and start running. And so there's our original frequency. Now the scale of this waveform is changing, right? As we go out further, it keeps compressing this, but that's not the interesting part. The interesting part is if we look at, the waveform, the time that it takes to go low and high and then low again is getting smaller. Over here it took, 300 some microseconds, and out here it took, less than 100 microseconds. And this last waveform was really, really small, and then all of a sudden it got big again. Why did it get big again? What happened at that point?
Did it overflow?
The counter overflowed. The count's controlling our frequency, and we added 10 to it. It was getting really high. It was up to say 250, so it only takes 6 cycles to interrupt. But then when we add 10 more to that, it's 260. Well, that overflows back to 4. And now it takes, you know, all the way from 4 up to 256, 200 some cycles before it interrupts. So we're back to this big long waveform. And if you get this out past 10 milliseconds, 10,000 microseconds, then it'll stop changing the scale. It'll just start sliding it. And here you've got a really, really nice view of what's going on, right? So if your lab was to create a waveform whose frequency increases, right, over time, well, this is a really nice demonstration of that, right? From here to here, the frequency gets higher and higher and higher, and then all of a sudden it resets and goes back, and so on. So the logic analyzer is going to be really useful. And like I say, it might not be as useful when you're developing your code first and you're trying to figure out the basic timing mechanics and, you know, is my prescaler correct and so on and so forth. Getting the actual table of numbers from that stopwatch tool will probably be more helpful. But once you think you've got it running and you want to see the higher level behavior, the logic analyzer can be really useful. And you can come in here and you can add other signals. So let's say I wanted to look at RB6 also. Right, I can put that on there. And I'll get a second trace down here for RB6. And it's color coded. You can change the colors and all kinds of stuff. But all right, questions about that? This is the first lecture this summer that I haven't felt like I'm totally running out of time, because we've still got like 45 minutes and we're ready to start talking about Lab 5. All right, so let's do it. All right, so Lab 5, you're playing with the timers and you're using them to do pulse width modulation. You have to use the timers in here. Okay, technically you can make this lab work without using any of the timers, right? You can just use delay loops like we used in some of the earlier labs. You got to use the timers. Okay, that's a requirement. And so objective, apply timers to scheduling tasks and implement pulse width modulation. Okay, it's going to be a single experiment again. So here's some sample code, right? You can use this along with the sample code we've been developing in class, in lecture. Location 0, we jump down to our main code. Location 8 is the interrupt, so we go to a high priority code. And if we have a very short interrupt routine, we can put it right here at location 8. But remember, you only have 16 bytes between location 8 and location 18. And so it's usually good practice at location 8, just put a go to. Just go to wherever you're going to write your high priority code. And then you can put your high priority code anywhere in your memory that you want, right? And we've only used 4 bytes for this go to. We've got some headspace there before we get to location 18 and so on. Same thing up here. If we had a bit of initialization to do in the beginning, we could put it right here, but usually location 0, just go to wherever your main code is. So the main code, right, has some state variables. We'll talk about those. Sets up addcon1, sets up tris-a to be mostly inputs, but bit 0 is an output, so that's FE. And when you're doing bit patterns like that, remember you can do, you know, a B quote and put your number in binary, and that can be easier to read sometimes when you're developing, but you know, you want to move towards being pretty comfortable with hex, so you can do 0xFE. And after a while, when you look at this, you see that, right? It's an automatic translation. You probably don't want to do decimal 254 unless you're just trying to be super tricky, because then that's a little harder to convert to this. But either of those is good. So we're not going to worry about the OSCON. In fact, I would say do not set this up, because we know that mplab is already running at 1 megahertz instruction clock. System clock of 4 megahertz. So you don't need to do that. All right, and then what do we do? And this is where I've mentioned that the comments in these labs I prefer not to see. I would prefer to see global interrupt enable high and global interrupt enable low. Because since we're setting up priority levels right here, we're not really talking about peripheral interrupts. So global interrupt enable H, global interrupt enable L, right? Enable low priority, enable high priority. All right, turn on timer 0's interrupt enable. Set timer 0 to be high priority. I guess you can make it high or low. Cool. All right, turn on priority levels. Clear the interrupt flag, because remember, timer 0 is always running. It's probably already requesting an interrupt. So clear that flag. And then load the magic value into the configuration register, T0con. And I'd like you to stick to the habit of, instead of figuring out a magic number, just set and clear the bits that you care about. Right, so bit set, you know, T0CS, or bit clear T0CS, and bit set PSA, and so on and so forth. Magic numbers, they take less code, they run faster, but they are a nightmare to debug. And if you wanted, you know, 81 instead of 41, it's probably going to be hours before you figure that out. Because we usually get so in our heads about the logic of our code and the algorithms, and this should be happening and it's not, and so we go and we watch videos and we start reading online and all this kind of stuff. And it's just that, you know, you did an 81 instead of a 41, but by the time you figure that out, you've probably like shattered your confidence in assembly language programming. You've probably changed your code 50 times to where it's not going to work correctly anymore, and it might have been correct to begin with, and you're probably frustrated and tired and hungry and so on and so forth. So that's my sales pitch, right? Stick to the mnemonic names for the bits in the registers. So set up the configuration register, and then this is clearing timer 0L, because guess what? 256 counts gives you a 1 millisecond delay. And that's not correct. Oh, it is, because you set up a 4-to-1 prescaler. Okay, so let's look at this math here. Let's look at timer math. So your instruction clock is 1 megahertz. So your instruction period is 1 microsecond. Okay, the reciprocal of 1,000,000. This code in this sample is trying to set up a timer to go after 1 millisecond. Okay, so we want timer 0 interrupt after 1 millisecond. Okay, how do we do that? What's a millisecond? That's 1,000 microseconds, which is 1,000 instruction cycles. So all these things we said about timer 0 in the beginning, right? These different ways that we can control it. We can use the initial value, the prescaler, the number of bits, right? We need some combination of those so that we get an interrupt after 1,000 instruction cycles. Well, one way to do this would be to make a 16-bit register. And initialize it to the overflow value minus 1,000, which is 64,536. That's a great way to do this. And prescaler is just 1-to-1. Another option is make this 8 bits and initialize this to 6, the timer register. So it will interrupt after 250 increments and make a 1-to-4 prescaler. So every 4 instructions it increments. After 1,000 instructions, it will have incremented 250 times. This will be 256 and it'll overflow. So this would get you 1,000 microseconds, which is 1 millisecond. In the sample code, though, instead of initializing this to 6, we just go ahead and we initialize it to 0. Now it takes 256 increments, times 4 is 1,024 microseconds. So this code doesn't actually increment after a millisecond, it increments after 1.024 milliseconds. Close enough, right? We're not that worried about it. So by clearing timer 0L, we'll get an interrupt after approximately a millisecond, and in our interrupt code, we don't need to reload a magic value into timer 0L. We don't need to load a 6 back into it. It's going to reset to 0. So that's what's going on here with this initial value. So it's an 8-bit, it's using the internal clock, and it's a 1 to 4 prescaler. And then we initialize it to 0. And then here's the main loop, just kind of hangs out here and spins. When we get an interrupt, we jump down to this high priority code. All right. Generally, you know, if we're writing a code, if we're in complete control of the system and the only source of interrupts is timer 0, we know when we get to our interrupt code, it's timer 0. But in general, right, if you're working with other people, if you're working on a larger system, if you have more interrupts, you may not know that. So usually the first thing you do in an interrupt routine is try to figure out what caused the interrupt. All right, so there's a bit test file on skip if clear. So check timer 0IF in intcon, and if it's clear, then we just come to this done, this exit point, which clears the interrupt flag and returns. But if that interrupt flag is set, we don't skip, we jump down to our interrupt code. This is where we handle timer 0. All right, so what does this code do? We increment state LSB. So every time we get an interrupt from the timer, this state LSB, least significant byte, is going to go up by 1. What's going on with these 3 lines of code? What do you make of those? Other than the fact that I can't highlight 3 lines of code successfully. There we go. What's the result of this test file and skip if 0? Just like in plain words.
Is it checking for like an overflow?
It's checking for a 0, but yeah, effectively for an overflow. This instruction says check this file register, and if it is 0, skip the next instruction. So we increment state LSB, and if it's not 0, which is going to be the case most of the time, we do the next instruction, which says branch to high priority done. That's our exit code. Clear the interrupt and return. But if when we increment LSB we happen to end up with a 0, this test will be true. It will skip the branch, and what do? We increment MSB. And then we toggle RA0. So the effect is we've got an 8-bit processor, but we're doing 16-bit arithmetic. So we increment this, it's just a plain old 8-bit register. We increment it, add 1 to it. Eventually, when we increment it from 255, it'll go back to 0. And when that happens, we'll go ahead and we'll increment this most significant byte. So this is acting like a 16-bit register now that we're incrementing. Because how do you increment a 16-bit number? Well, add 1 to the low 8 bits. And if that makes these bits 0, you've gotten a carry out of this 8th bit. Go ahead and increment this. That adds the carry to that next bit position. So this is all a manual way of doing 16-bit arithmetic, and every time that we increment that most significant bit, we toggle port A. Well, we're incrementing every, so we get an interrupt every millisecond. And we increment most significant byte every 256 interrupts, which is 256 milliseconds, which is a quarter of a second. So this code will toggle RA0 4 times a second. So you can load this in, you can play around with it, you can use it to explore the stopwatch and the logic analyzer. You can use it to explore, you know, the configuration register. You can change the prescaler. You can load different initial values in, and so on and so forth. So that's good sample code. All right. So use that to warm up, and then you can go ahead and pursue experiment 1. So experiment 1, you're generating a waveform that exhibits pulse width modulation. All right, and this is pretty simple to put on paper. It's 1 page, but it's kind of flippy floppy. You read it 5 times, you can come away with 5 different impressions of what you're supposed to do. So let me see if we can nail this down the first time. You're going to generate a waveform, and your waveform is going to go on RA0. So output waveform on RA0. There's the lab police coming by. And we'll come back to this first sentence. This is actually like the least important part of the whole thing, so we'll come back to that in a minute. Let's just start from here. Additionally, the code generates a PWM signal on RA0 with a frequency of 250 megahertz, a period of 4 milliseconds. All right, so we want a waveform on RA0. And we want this to always be 250 hertz, which means the period is 4 milliseconds. All right. Additionally, you're going to use pulse width modulation to change the shape of this, to go from something that's high all the time to high 75% of the time, then 50, then 25, and then off, and then back to 25%, 50, 75, and 100%. So over time, the duty cycle of this waveform is going to change. It's going to start off, you know, high all the time, and then it's going to be high for 75% of the time, and then it's going to be high for 50% of the time, and then it's going to be high for 25% of the time. I'm totally messing up my waveform. This is where graph paper would be your friend. And then it's going to be high for no percent of the time, and then it's going to go back 25%, 50%, 75%, and then back to 100%. All right, when do we change the duty cycle? Change it every half second. All right, power level is another word for duty cycle, right? It's how much power we're delivering to the system. So first you generate a waveform at 100% maximum power. That's just a constant 5 volts. Do that for half a second. And then generate your waveform, same frequency, 250 hertz, at 75% power. Do that for half a second. And then go down to 50%, 25, and so on. So the synopsis, this is RA0. So 100% duty cycle for half a second. And then do a 75% duty cycle. And the same frequency for all of these, 250 hertz, do that for half a second. And then do a 50% duty cycle, 250 hertz, for half a second. And then a 25% duty cycle, 250 hertz, for half a second. And then a 0% duty cycle, 250 hertz, half a second. And then go back up 25%, 50%, 75%, then go back up to the top. Each of these is a half second. All right, the 100% duty cycle, this is just constantly on. There's no waveform that you can actually see. It's just going to be high. The 0% duty cycle is just going to be constantly off. It's going to be 0 volts coming out. But the 25, 50, 75%, you're going to see a waveform going up and down 250 times a second with, you know, whatever percentage of high time versus total period your duty cycle is requesting. And it's going to run at that duty cycle for half a second, and then another half at the next duty cycle, another half at the next duty cycle.
I am a little confused about what we're supposed to be changing in order to make this happen.
So, all right. So is everyone good on the goal? And then we can talk about implementation. Goal is good. Okay, and it's all in the lab, right? So how do we do this? We have, you know, some mplab code, for example, that we were doing here that generated just something that was high and low, right? And how did we make it generate high and low? Well, we got an interrupt, and we loaded a value into timer 0L, and we went back to our loop, and then when the next interrupt occurred, we toggled the output value, went back to our loop. When the next interrupt occurred, we toggled the output value again, and every time we toggle that output value, the output switches between high and low. Well, in this case, you know, every time that we get an interrupt, we always reset timer 0L to the same value. But what would happen if we loaded in different values depending on whether our output was high or low? For example, if the output was low, we could load a 200 into here. But if the output is currently high, we'd load a 100 into here. Well, when the output's high, we load a 100. It's going to take a long time to interrupt. And then when the output's low, we load a 200. It's going to take a short time. That's going to be a waveform that's going to be high more than it's low. It's going to be a higher duty cycle. So you're doing this purely by hand, right? This is just kind of bare-fisted manipulation of the hardware. And you need to keep track of some information to make this happen. So how could we do this? Let's do some pseudocode. Suppose I said high time equal to 100 and low time equal to 100. And in my interrupt code, I'm going to, you know, increment a counter. Alright, so I'm going to increment some counter that's going to start off at 0. And I'm going to do the following. If counter equals high time, so if I've hit my high timer, I'm going to do the following. Turn output off. Reset the counter. And, you know, ret fee. Alright, this is basically the code we've been playing with in mplab today, right? I bump up the counter and well, let's do this differently. let's take advantage of the hardware. So forget that. New approach. So let's look at our interrupt code. If output is on, set timer 0L equal to 100 and turn the output off. Else, if the output is off, set timer 0L equal to 200, turn the output on. So there's our whole interrupt code. Okay, let's just think about what that's going to do. Suppose the output is off. Okay, so our output waveform is off. And we get an interrupt. Alright, if the output's off, we're going to set timer 0L to 200 and turn the output on. So the output's going to be on. We've loaded the timer register to 200. It's going to take 56 microseconds, let's say, before we get another interrupt. So this is going to be 56 microseconds. We get an interrupt. Our code in the interrupt handler is going to say if the output is on, set timer L to 100 and turn the output off. So that's going to turn the output off, and it's going to load a 100 into timer L. Well, the next interrupt's going to occur when this counts up to 256. That's going to take 156 microseconds. So this output will stay low for 156 microseconds. And then we'll get another interrupt, and our interrupt code will say if the output's off, turn the output on, and set the timer to 200, so it'll take another 56 microseconds before it turns off, before it interrupts, and then the interrupt will say if it's on, set the timer to 100, and so on and so forth. So this is about a 25% duty cycle, right? It's on for 56 out of, I think it's 212 microseconds. And I got this simply by choosing these two values. Now, if these two values were the same, I would get a 50% duty cycle. If this value was a lot smaller than this value, then this on period would be a lot longer. It would be a much lower duty cycle. If I made this 200 a lot smaller, then it would be a much higher duty cycle. It would be on and then off for just a little bit of time. So the analysis part of this before you start writing any code is thinking about how to generate these waveforms. And remember, we're not just interested in duty cycle, we're interested in frequency. All of these waveforms have to be 250 hertz. Right? So it has to go up and down 250 times a second. So 4 milliseconds for one cycle. So from here to here we want 4 milliseconds instead of 212 microseconds. So you're going to need to play around with, you know, how do you set up your prescaler? Do you want an 8 or 16-bit register and so on? And then pick some values to put in here to generate whatever duty cycle you want. And maybe make yourself a table on paper that says, you know, if I want a 50% duty cycle at 250 hertz, here's what I'm going to set my timing values to. If I want a 25% duty cycle, here's what I'll set my timing values to. These two are easy, the 100 and the 0. 100 just turn the output on, 0 just turn it off. There's no alternating back and forth. But these others you need to alternate. But you also need to do something else. Every half second you need to change these numbers to change your duty cycle. Well, a good way to do that is to set up another interrupt. Set up another timer that will interrupt you after a half second and use that interrupt to adjust these timing values for your pulse width modulated waveform. So this is huge on, you know, planning up front. Before you ever write any code, before you ever go into mplab to start working on the actual code for Lab 5, you're going to spend a lot of time just playing around on paper and looking at waveforms and thinking about how you're going to do this interrupt handling to drive an output high and low.
Do you mind keeping all of that paperwork just so I can ask you questions after class?
Sure.
Thanks.
I have a question as well.
Yeah.
So, since we're dealing with like a lot of time, I'm guessing it's going to be a lot of single stepping. So, how do you kind of skim through that? Do you use that play icon that you were doing from earlier, where it loops through the code, or?
Yeah. So as you're developing this, probably all of this is interrupt driven. So probably a good thing to do is throw a breakpoint at the beginning and or at the end of your interrupt code. And at the beginning of your interrupt code, if you expect your timing parameters to change to give you, say, a 75% duty cycle, you hit a breakpoint at the end of your interrupt code before you return, and you can check, what's been set up. What are the values in timer 0, L, and H if you're using H? How have you adjusted your flags, and so on and so forth. If there's a problem at that point, right, go back to the beginning, hit the breakpoint at the start of the interrupt routine, and then you're going to want to single step through and figure out, okay, so I wanted to check a variable and see that I was in this state, and then make these changes and figure out where the problem is. And everything happens in your interrupt code, right? Your main program is more or less going to be the same thing as what's in the sample code, just a loop that just spins, and it's just waiting for interrupts to handle.
Thank you.
Yeah, you're welcome. All right, so let's talk about state machines. Because this is a state machine, right? When you get an interrupt, what are you going to do? Are you going to wait 100, set your timer to 100? Are you going to set it to 200? Are you going to set it to 15? Are you going to change to a 16-bit? You get an interrupt, you're going to come to the same spot in your code, location 8, it's going to branch to some location, but what you do at that point depends on what? The state of the system. And the state is basically, right now I'm at this point in my pattern of duty cycles, I just finished 25%. Now in my interrupt code I need to change things so that I generate a 0% duty cycle. Or, you might be at this 25% duty cycle, and when you get an interrupt, what do? You change to a 50% duty cycle. So you need to know not only your current duty cycle, but are you in the process of decreasing or increasing your duty cycle every half second? So you need to know where you are in this pattern of duty cycles. And this is all the notion of state. This is what the flip-flops do in a state machine in 250. In programming, we don't need flip-flops, we use registers, variables. And so here's one way to do this. You don't have to do it like this, okay? This is just a suggestion. Well, it is a suggestion, but I'll say a possible suggestion, right? You could have something called, state. And you can use state to tell where you are in this pattern. So state 1 means I'm at 100% duty cycle, and after a half second I'm going to go to 75% duty cycle. State 3 says I'm at 50% cycle, and after a half second I'm going to go to 25. State 7 says, yeah, I'm at 50% duty cycle, but next time I'm going to go up to 75. And so every half second, what do? You increment your state variable. It's just a file register. If you happen to increment it to 9, set it back to 1, right? So that from this state you go back to this state. And then use this state variable inside your main interrupt code where you're trying to decide what should I set timer 0L to, or H and L, right? Based on, I'm in state 3, it should be a 50% duty cycle. I'm in state 4, it should be a 25% duty cycle. It's very easy to do once you've done it, right? Once you get this working, if you step back and look at your code, you'll say, oh, that's actually pretty simple. But wow, getting there is really, really challenging. right? It's a lot of setup. But think about how you would do this in pseudocode or a flowchart, right? Think about how you would write C code to do it, for example, in terms of, you know, having a state variable, in terms of some if statements and so on. And you also need to bring in, you know, the realities of the PIC processor and the fact that, you know, we need to use these timing registers to set up interrupt periods and so on. But you can make that happen. And then there's one more detail, just because that's not enough to give you a lot to do. So there's one other detail, which is RB0 should toggle every quarter of a second. Alright, well, how do we do that? Well, you could use a third timer if you wanted. You could set up a third timer to interrupt every quarter of a second, and on that interrupt, just toggle RB0. Or, you know, instead of using a half-second interrupt to change your duty cycle, you could have a quarter-second interrupt. And every time that you get that quarter-second interrupt, toggle RB0. And every other time that you get that quarter-second interrupt, go ahead and change to a new state. And there's probably other ways to do it too. Alright, so we got like 3 things going on. First thing going on is your output is going to be toggling at 250 Hertz. Second thing going on is that the duty cycle is going to be somewhere between 0 and 100. Third thing going on is that duty cycle will change every half second according to the schedule. And then the fourth thing going on is that RB0 will be toggling twice for each half second, every quarter second. So this is definitely an experiment you want to build up in pieces. Right? Don't write 1,000 lines of code and then try running it for the first time. Break it into little pieces and try to get those little pieces working first. First thing you might want to do is just generate a straight 250 Hertz signal, 50% duty cycle, on, off, 250 times a second. That gets you your initialization, your interrupt setup, your interrupt handler, your initial code working with the timer registers. It gets through all of the learning pains of the configuration register for T0 and so on and so forth, right? So maybe get that working first.
It seems like as you get further into your program, you need to tune the timing more and more because you have more instructions, right?
Well, technically no, though, because, right, if we were using delay loops, that would be absolutely true. But because we're using the timing registers, right, if in the beginning of your interrupt code you load the desired value into timer 0, L, and H, then it doesn't really matter how much other things you do in the interrupt code, as long as you get out of there before the next interrupt occurs. And at a 25% duty cycle, right, this high or low time is going to be a millisecond. Okay, that's 1,000 instruction cycles, so you got a lot of time to play with. So because we're using the timing hardware, we're kind of immune from you know, complicating our timing based on the code that we write. Delay loops, it's a whole different story, right? The more code you write, the more time it takes, the more you have to tweak your numbers, and that's just, you know, you end up chasing your tail all afternoon. So this is one reason why we have timing hardware inside processors. Makes things a little cleaner to develop. Alright, so yeah, maybe try to get a basic waveform out first at 250. Well, try to get any waveform out first, and then try to dial it in to be around 250 Hertz. None of this has to be exact. I don't care if it's 240 Hertz, I don't care if it's 270 Hertz, right? But I'm looking for general, you know, behaviors here. Something that, you know, basically follows the schedule. I don't care if it takes, you know, 0.512 seconds, which is what the lab says. Right? 0.512 seconds is nice because that's an overflow point for, you know, a binary counter. 0.256 is nice if you interrupt every millisecond. It's 256 interrupts, right? But I don't care if you know, it's not exactly that. I also don't care if you go straight from step 8 back to step 1. So go 100, 75, 50, 25, 0, 25, 50, 75, and then go back up here for 100. Technically, the way this is written, you would stay at the 100% maximum power for 2 steps. I don't need to see that. I think it's cooler if you skip step 9 and just go, you know, exactly like this. But again, I'm not going to worry about it. If you can do, you know, any version of this with any timings, you know, close to this and this and this, you're good. Right? We're after the higher level themes here. All right, so yeah, try to get a waveform going, try to dial it in around 250 hertz, and then maybe start playing with duty cycle variation. Try to figure out what you have to set up to do a 25% duty cycle, or a 75%. 25 and 75 are going to be really close to each other, right? The only difference is 25, you turn it on for a short period, off for a long. 75, you turn it off for a short, on for a long. But the timing numbers will be exactly the same. 100 is just on all the time, 0 is off all the time. So you really only have one tricky timing to figure out after you've done a 250 hertz, which is, you know, let's do a 1/4 or a 3/4 duty cycle. And then once you have that figured out, start thinking about state transitions. Right? Think about how am I going to keep track of stuff and what am I going to put in my interrupt code to do whatever I just discovered I need to do to make, say, a 75% duty cycle. And then it's a matter of, you know, in your interrupt, go ahead and do this bump up. Now go ahead and you know, set up your half-second interrupt to get this working. And then after all of that, I would say go ahead and add in this toggle of RB0. And if you want to use a third interrupt, that's a fun thing to do with that. If you want to try to use PR2, so you can just set it up and forget about it. I don't know if you can get 1/4 of a second out at a megahertz. I don't think you can. But you can do some other stuff. Right? The one caveat is if you use 3 timers, you're going to have to do a little more work in your interrupt code. If you use 2 timers, you can make one high, make one low. You're going to vector to totally separate locations. If you have, say, 3 timers, maybe 2 of them are going to be low priority, where you're going to have to do something like this, which checks to see which interrupt flag caused me to be here. But that's not too hard to do, and it's a good thing to be able to do. All right, let's take a minute or two and talk about the write-up. So I need to be able to look at your lab report and see what you see, which convinced you that this was working correctly. I'd like this in the form of waveforms. So using the logic analyzer, what I'd like to see is, you know, a little bit of discussion, right? So you know, the output starts off at 100% duty cycle. Show me your waveform trace where, you know, this is RA0. Show me your waveform trace for some period of time, not 1 microsecond, right? But some long period of time where this output is high. Now this whole thing is going to, you know, be at 100% duty cycle for half a second. So you should be able to show me a big long timing window where this is 10 milliseconds. That's the widest window we can see in that logic analyzer. 10 milliseconds of this output being high. All right. And then, you know, run your code until it changes the duty cycle and get some waveform where it's doing the 75% duty cycle. All right. If this is 250 hertz, that's a period of 4 milliseconds. Our logic analyzer display is 10 milliseconds max. So wherever your waveform happens to start in this 10 millisecond window, you should be able to capture an entire waveform, low, high, low. And, you know, you might luck out and catch, you know, 2 waveforms in there or something like that. But you're guaranteed to have at least one complete waveform, which means a transition from low to high, a transition from high to low, and a transition from low to high. All right? I want to see that logic analyzer output. And I want to see a complete waveform. So don't do this. If you give me a logic analyzer output that looks like this, can I tell what the duty cycle is? Can you tell what the duty cycle is? Absolutely not. Because I don't know how long this went to the left, and I don't know how long this went to the right. So this tells you nothing about the frequency or the duty cycle. So you don't want to do that. If you have your logic analyzer output and you see something like this, does that tell you the frequency? No. Does it tell you the duty cycle? No. Because I know my waveform started here, but I don't know what happened after this point. So that doesn't work either. And if you do a logic analyzer window that looks like this, does that tell you what you need to know? No. I know that my high period was this, and I can look at the numbers on the axis, and I can tell how long my waveform was high. But unless I know how long it was low, I still don't know the frequency or the duty cycle. So to make this graph meaningful, you've got to have at least one more up here. In other words, you've got to have something that lets you see how long it's high and how long it's low. Which means I need a transition up and down and up. Or, you know, I need a transition down and up and down. That would also work if your logic signal output looked like this. Right? That's enough information to tell both frequency and duty cycle. Because I can look at this point, and I can look at this point, that's a period. And then I can measure this, and that's the time that it's on, and I can take that ratio, and that's the duty cycle. So make sure when you put this into your lab report that you've got enough information that you captured. And like I say, if you capture 10 milliseconds of information, and this period is going to be 4 milliseconds, guaranteed there's enough information there to see one of these waveforms. All right, so put that in your report. Make sure that the x-axis is legible, right? So that you can read what the time scale was, and you know you can make this big. So you can blow it up like that. All right, so show the waveform at the 75% duty cycle, and then, you know, breakpoint when you change duty cycle. Next time you change duty cycle, go into the 50% and show me the next waveform. And then 75, 0, or 25, 0, 25, 50, 75, and back to 100. So you're going to want at least 9 screenshots from the logic analyzer output. And by looking at the x-axis on those, I should see that the time from one plot to the next was about half a second. If you capture each of these either like at the beginning of your new duty cycle or at the end, the time on that x-axis should be half a second from the previous graph's time. Right? So that will demonstrate clearly that, you know, this is doing the thing it's supposed to do.
So the one program is supposed to change duty cycle that cycles 8 times, or 8 separate programs changing duty cycles.
It's all one program.
Okay.
And that one program will generate the waveform at a given duty cycle. It will slowly change the duty cycle every half second, and for extra kicks, it will also toggle RB0 every quarter second. Now for RB0, this is so much faster than what the waveform is doing, which is 250 Hertz. I would do a totally separate test run just to capture RB0's behavior. And for that one, the stopwatch can work really well. put a breakpoint every time that RB0 toggles. And when you hit that breakpoint, you'll see a new time in the stopwatch window, and you can see port B in the variables window, right? Take a screenshot. Go to the next breakpoint, see what the time is, see what the value of port B is. Do that maybe 3 times to show it, you know, high and then high, or low, high, low, with the corresponding stopwatch time displayed and the port B displayed, and you're good to go. So this is an unusual lab. Probably the least amount of your time is going to be spent writing code, right? The biggest bulk of your time is going to be the setup and design in the beginning, dialing in the numbers and the configuration register settings and all that kind of stuff. And then the next big chunk of time is, once you have it working, capturing the results and putting it into a report. And the time you actually spend putting in code is going to be pretty minimal. Debugging can be, you know, a huge amount of time, depending on how well it works the first few tries. All right, that's lab 5. Did I give you a week for that? I probably gave you a week for that. It's a long lab. It's got a lot of steps. Started early, started like right now, and come into lab and ask questions, right? And if you haven't finished this by Tuesday, you should be really close by Tuesday, so that if you're not finished because you don't know how to get something to work, you can come into lab on Tuesday, and I can watch what you're doing in mplab, and I can give you some suggestions, right? That's going to work better, I believe, than watching, you know, 20 random YouTube videos of people talking about timers on PIC chips, because this is a very particular thing we're after here. And if you can stay focused on this task, right, and let your debugging time go into, well, I can't get a quarter of a second because, you know, my prescaler isn't working, right, that's going to help you the most as far as the course goes. So start this soon. Come by right now, you know, in office hours if you have questions, and try to finish it by Tuesday, and then come in lab hours on Tuesday, or ask questions in class on Tuesday, either way.
So we're going to use timer 2, right? Because pre and post scalar?
It's your choice. So you got 4 timers. I'm happy with any or all of them that you want to use. But you have to do all your timing with timers, no delay loops. Timer 0 is certainly going to be one of them, I would think, just because it's the most versatile. Timer 2 might be good for RB0 or for that quarter second, that half-second interrupt or something like that. But you got to play with the numbers, see what you can get out. I don't think you can get a quarter second out from timer 2 directly, but you know, if you can generate, you know, 1/100th of a second interrupt, well, then all you do in your timer 2 interrupt code is you just add 1 to a counter, right? And when it gets up to 25, you know a quarter second has passed. So reset it and do your quarter second routine. And that's part of what happens in the sample code. This code generates an interrupt every millisecond, but it waits until you've gotten 256 interrupts before it toggles this bit. So the interrupt bumps this up. You don't have to worry about this counting the most significant bit stuff. That's just extra fun in here. But you know, this can be used to say, hey, a millisecond has passed. Do I want to do something? Well, bump up a counter when it hits some value. Okay, now I want to do something, so go do it. So, but yeah, you get to choose how you want to use the timers and which ones to use. All right, I am done talking. Thanks for the extra 8 minutes. I will post all of this on YouTube, and I will switch over to my office Zoom. Come by if you want to talk about your previous lab or this lab or anything else. Send me one final attendance ping, and I will see you in lab, or I will see you next time. I'm going to crank my AC for like 5 minutes. All right, have a good one.
Thank you. Have a great day.
Thanks, you too.
See you in lab.
All right, see you there.